So these two videos we prove the standard two important quality in vector calculus, and the one is the if you take sorry, not this what I'm writing about. So basically, the first one is if you take the gradient of a function and you take the curl, it becomes zero. Okay, so the second one is if somebody take a divergence on a curl, it should be vector function, it will be zero. Okay, so if you basically this is like a cohomology. If you don't know about cohomology, then it's fine that I mean you can forget about what I'm saying. But basically, if you learn about differential geometry, basically you can understand this gradient or curve or some these operators basically are just the differential in differential form. So basically, there is a thing called Poincare lemma. Okay, so I will show this in other videos, but today we just try to prove it in a very elementary way. Okay, so the elementary way is just first we prove this. Okay, so the easiest way is we just brute force do the computation, or we can involve the epsilon delta. Okay, so remind you guys that delta phi just take a partial of phi I and take an ei. So I use ei as the basis. So I is from 1 to 3. Okay. And how about if you take a vector value for this? So if you take an epsilon I, then the answer will be okay. So this is just partial x, partial y, partial z, a x, a y, a z, and I call E1, E2, E3. Okay, so basically this is just EI and partial j k, partial k a j, and I you just change your ijk. So finally you can see it becomes this just I from 1, and you change 2, you just change from you just change ijk, there will be a permutation. So finally the result just this. I mean there are 6 terms, right? But you just do the expansion. Okay, so this is the form what we need. Hopefully this is correct. So we have 6 terms. So the first term is E1, Y, and Z. So it's X, Y, Z, right? Nice. Okay, so from here, then we can start to do the calculation. So this is this. Okay, so I omit. Okay, so finally, all we need to do is just change this as our AK, right? As our AK. So what we have is just EI partial J and partial K phi and epsilon ij. Okay, I use the lower variable ijk and ijk. ijk partial j partial k phi and ei. Okay, but notice that this is anti-symmetry, this is symmetry. So basically we have this. Suppose you sum jk, then this is the same as you change k to j. You change k to j because okay, so let me write slowly. You can change I and k and j, and this is the same, right? This is just the definition for this. Okay. But the problem is that if you change this jk, then so this is just the definition of this. But from this, you can relabel the j and k to be kj. So this is just relabel. But when you relabel k and j, and then these two are still the same because the second derivative can be changed. So this is just negative. So you see these two terms are negative to each other. So which tells you that this term is just 0. This term is just 0. Okay. So from here, what we need is this is so the basic result because this is anti-symmetry and this is symmetry. So we'll get 0. So this is similar as you do as you expand the results. Okay, so let me summarize that the formula we have, then we can do more. So this is the formula we have. Okay, so now we already proved this. We prove what? We prove this. Okay, so then the second, what we want to prove is the detect divergence. Okay, by the way, the divergence acts on a vector component, just partial IAI, right? You just this. Okay. Okay, so now the result is similar. For this one, we take this. So this is just this. Oh, this is IJK, IJK, epsilon IJK, partial JKEI, right? And so for this one, we just take a derivative I. So just sum over I. Because for the I component is sum over JK. So we take derivative I, sum of I and the JK and the partial I epsilon I JK, partial JAK, right? And then you'll see basically you get IJK, epsilon IJK, partial I, partial J, AK. So you see it's exactly the same. This is anti-symmetry respect to JK. This is symmetry respect to JK. Okay, so sorry. What I'm saying about this is a symmetry respect to IJ, and then this is anti-symmetry respect to IJ, anti-symmetry respect to JK. Okay, so what we have is this. So anti-symmetry with respect to this, and the partial I, partial J, and anti-symmetry respect to this. So the same reason, which is 0. You can do the because when you change IJ, then you will change the there's a will be minus sign. Okay, but the second term is symmetry. Okay. Okay, so now we prove these two. Okay, I think it's enough for this video. So the summary is that basically we prove these two. Although these two are very easy identity in the vector calculus, but they have the deep connections in cohomology theory. Okay, or the people so-called differential form or the de Rham cohomology. If I have time, I can talk it. Okay, so this is a video what I want to show now. Okay, and the next time we will prove more vector identities. And be sure to subscribe to my channel. 6.